more example from section 4.1 because it's something that's going to build as we move into another section anyway. So though I had hoped that we had finished 4.1, we really had not. So just very quickly, in section 4.1, which we're talking about extreme values, here's one more example I'd like to do to kind of finalize it. And this is going to pick up what we call a piecewise function. And the question is, and so this is the last example from section 4.1, the question is to find your critical values, find critical values, which is set the first derivative equal to 0 and set the first derivative undefined. We've done that now pretty comfortably. See if there's any domain endpoints. And when you start talking about these domain endpoints, this is where you're thinking, do I have a square root function that's going to limit my domain, or did they limit my domain by giving me an interval that I was limited to in the beginning? And then to ask extreme values. And remember, when they ask extreme values, this question is the same as saying, do you have any local maxes and any local mins? That's this question, any local maxes or local mins, and then to also check for absolutes. And usually in Course Compass, they'll have a million questions underneath there, so you can't miss of knowing what it is they want. So this is kind of the setup. And here is what they've given me as your function. And it is what they call a piecewise function. Okay? It's defined in two pieces. Part of it's a linear function, 3 minus x, and part of it's 3 plus 2x minus x squared, which is a parabola. So they have to give you some parameters, and they say let it be linear when x is less than 0, and let it be parabolic when x is greater than or equal to 0. So there's the function that we're working with. It's a piecewise function. Now, anytime you're given a piecewise function, you need to kind of look at these little parameters. That 0 is going to have some issues. Something's going on at 0. These pieces of the function are meeting at 0. Are we meeting at the same place at 0? Is there a cusp at 0? What is going on at 0? That's where you're going to be kind of concerned. So they're asking for these critical values, and so you've got to watch this 0 stuff. Now, if you wanted to graph this, and I tend, when I see a piecewise function, the first thing I want to do is graph this sucker. If I wanted to graph this before I ever started to answer the question, just because I had a vision in my mind of what this is, well, if you look at the function 3 minus x, that's just a linear graph with a -1 slope and a y-intercept of 3. Right here, -1 slope, so it looks like this. Okay, that's the 3 minus x part of the graph. The 3 plus 2x minus x squared, that's a negative x squared graph, so that's a parabola that's concave down. But what's going on when x is 0? When x is 0, this is 3 plus 0 minus 0, so it's at a height of 3. So we're in agreement there that at 3 it's filled, and then it's going to do something like this. So right off the bat, I see there is a cusp in the graph. So the first derivative is not going to be defined there. This function is continuous, but this function is not differential over its entire domain because there's a cusp in it. But that's going to be a local min. The cusp is going to be a local min, and this is going to be a local max. And there's not going to be any absolute extremes because the end behavior is up on the left and down on the right. So then we come in here and think, okay, I'm supposed to answer this question. I'm supposed to find the critical values, which means set the first derivative equal to 0 and undefined. Well, you have to look at the two halves of the graph. When x is less than 0, your function is y minus x, and the first derivative is a -1. Now, this makes total and complete sense because it says the first derivative equals -1, which means the slope of the tangent line anywhere on the graph is -1. Well, the slope of the tangent line to the linear graph is going to be the slope of the graph itself. So that's perfectly logical that that derivative equals -1. And this, we go right into this into the next section, which says that when your first derivative is a constant, then you have a linear graph. Okay, so that's a linear graph. Okay, so now let's look at when x is greater than or equal to 0. So now I'm looking at the y equaling 3 plus 2x minus x squared. When I take the first derivative, this is 2 minus 2x. Remember, your focus is finding the critical values. Well, there's two places that critical values are happening. They're happening when y prime equals 0 and when y prime is undefined. Well, the undefineds happen with a rational or a radical, and you don't have a rational or a radical. There's nothing being undefined here. So you're strictly looking where your first derivative equals 0. or where 2 minus 2x equals 0, or where a negative 2x equals negative 2, or where x equals 1. So, you have a critical value at x equaling 1, and what's the deal with 0? Okay, from the graph itself, you know there's a critical value at x equaling 0. But how in the world do you recognize that? Right? Because if you'd never graphed this thing, you wouldn't catch that critical value at 0. So what I'm trying to emphasize is, hey, we got one of these critical values, but there's going to be two, because I can see it right there at 0. So what you have to be careful is noting when you have this parameter, you better be careful around this parameter. Okay? You have to be very careful. What in the world is going on at 0? So at x equaling 0, one of your y primes equals 1, and your other y prime at 0, okay, your other y prime at 0 is 2 minus 2 times 0, which is 2. So your y primes are not the same. Your first derivatives are not equal at 0, which means at 0, y prime does not exist. Y prime is not differentiable at 0. Y prime it's not the function is not differentiable at 0 because your first derivatives are not the same at 0. Right. Well, the limit exists, but it's not differentiable. So how about this? Y is not differentiable at x equaling 0, which means, therefore, x equals 0 is a critical value. Right? Where the first derivative is kind of undefined. The first derivative is undefined there because it's not the same from both sides. That's a critical value. So you have a critical value at x equaling 1 and then a tricky critical value at 0. So again, I want to emphasize when they give you a piecewise function, you pay attention to those numbers in those parameters because something's going on there all the time. So be very careful with that. So you have two critical values. And so your critical values, the answer to the question is my critical values are when x equals 0, when x equals 1. I don't have any restrictions on my domain, so there are no domain endpoints. But these do turn out to be the local maxes and local mins. So you end up having a local min at the point 0, 3, and a local max at the point 1. And what's the local max? 1 what? It'd be what? 3 plus 2 minus 1, which is 5 minus 1, which is 4. There you go. So be extremely careful with your piecewise functions and these parameters. You watch them close there because they can be tricky at those parameters. And it's always a good idea to graph it so you kind of have a vision of what's going on at those parameters. And so that's the last question, oddly enough, of that recording of that section in extreme values.